paper, and there's an issue with the proof. I think I'm not fully sure yet. I can't understand, so if we get there, maybe we can try to figure it out together. So the paper is called, it's a fairly it's a famous result now, at least in the crypto community, quantum crypto community. So it's called Quantum Pseudorandomness and Classical Complexity. This is by William Kretschmer. Okay. Okay, so this paper actually does a bunch of things. So what I'll do is I'll give you a quick, a very brief overview of what this does, and then we'll look at one part of it which is of interest to us. Okay, so the question that we are interested in this paper is the following. So it basically asks, what are the hardness assumptions one needs to have pseudorandom states, and which unlikely collapses so example P space equals P, or BQP equals QMA, something like that. Would invalidate the security of PRSs. Okay. So one is trying to see what is sort of the the assumption, the hardness assumption that we need to have PRSs exist. Okay. And what goes wrong if you're somehow able to distinguish pseudorandom states from actual hard states. So if you have that possibility, can you show that there is some strange collapse that happens in existing classical complexity? Okay, so you have some formal evidence that tells you that pseudorandom states can actually exist, right? Okay. So stated differently, which is what I just mentioned. So what computational power suffices to distinguish hard random states, from pseudorandom states? Okay, I should actually silent the. Okay, so this is fine. This is just essentially the same thing. We're just asking it in a slightly different language. Okay. Okay. So an obvious upper bound seems to be QMA. Okay. So what do we mean by this? So here what we mean is, suppose that Arthur holds many copies of psi, okay, Merlin gives the circuit C that produces psi. So you know QMA, right? So QMA is that there's a quantum verifier, and there's a Merlin. So this is Arthur normally in QMA, right? So the MA are Merlin and Arthur. There's probably some fairy tale which I didn't read as a child, so I'm not fully familiar with the story. But So Merlin is supposed to be the magician or whatever, and Arthur is like a classical being, or well, not classical, quantum, but normal. This is unbounded, and so the quantum verifier has some problem they want to solve, and they can ask the all-powerful Merlin to give them some to help them, right, in some way. So they can give a classical string, a quantum string, whatever. So if it's just a classical string, then it's called QCMA, C for classical, and otherwise if you're sending a quantum, if Merlin is sending a quantum state, it's QMA. Okay. And the set of problems you can solve using in such a setup with some bounded error is QMA or QCMA. Okay, so we will formally define QMA later, but at the moment this is the idea. Is it clear? I don't know if you're not familiar with this. You can ask. Are you?
Single round or
Yeah, it's one round. That is QIP. The one so that's interactive proof. So here you have just one round. It's just an analogous thing of the classical. Okay. Okay. So what are we trying to do? We're trying to argue that somehow you should be able to distinguish Haas states from pseudorandom states in QMA. Okay, intuitively, and then we'll see why it's wrong. But intuitively, let's see why people, why one might imagine that it's possible, because one can imagine Arthur holds many copies of psi. Okay, and what Merlin can do is Merlin can give a circuit C, okay, that produces psi. Okay, so now
so these PRS are defined with respect to like BQP. Like
this we already did in the.
so
It's the same notion. We didn't change anything. So
no, I'm just asking.
the
So
distinguisher.
PRS are like pseudo-random state which are indistinguishable from hard-random state.
For computationally bounded, which is BQP, yeah, exactly. Is that okay? Yeah, you can take uniform, non-uniform. I think there are small subtleties over there, but other than that, yeah, there's not. Okay, so right, so Merlin gives the circuit C that produces psi, okay, and Arthur just does a swap test. So Arthur does a swap test between psi and C acting on zeros, right, because it will produce the state. And so here are some obvious observations, right. So clearly, if the state is Haar random, there is no such circuit, right, because the circuit would be exponential in size in general. So, and if psi is indeed PRS, then there exists an efficient circuit, right, by construction. So this can be sent, okay. So if psi is PRS, such a circuit exists, right, of polysize, and if it's hard, then it doesn't. No circuit exists. Okay, and so this basically allows us to do what? It allows us to somehow distinguish using QMA, right? So thus PRS, it appears is in QM, okay, but
So this circuit C is polynomial in size is assumed.
it's just by definition of a pseudorandom states, right? Because pseudorandom states have to be efficiently preparable.
When you say for Haar there is no circuit, then you mean polysize circuit.
Yeah. Right. I'm sorry. No polysize circuit. Exactly. Thank you. Right. This is fine. Okay. And okay. So what seems to be the problem here in the argument? Do you see any gap in the argument? What could be? Any guesses? It has to do with the definition of QMA. So, how do we define complexity classes? Normally we define it using strings, right? We say whether a string is in the language or not, right? But here it's not a string, right? We're asking whether the state psi is in the language or not. So it's not quite QMA, because QMA is defined for strings. This is defined on quantum inputs. So the class is a little bit different. So if you want to connect it to standard QMA, you still need to do some work. It's not immediate. Okay, so that's the subtlety. So Arthur is getting a quantum input. Okay, so that's why this question is not immediately answered. Okay, one might think there's an immediate answer, but it doesn't really work because of this subtlety.
So, yeah, go ahead.
Can we define the language to contain string, where each string is the description of the circuit that prepares it? Because the description.
No, but then you won't. Then you can't phrase this question, right? Because a hard random state would require an exponential size string. It won't even.
Yeah, but we have an exponential depth circuit, but which has a polysize description.
Exponential depth. So the number of gates would already be exponential.
No,
No?
like I'll just read apply Hadamard 2 to the n time. So now I've described to you a circuit which was exponential depth, but I could describe it in polysize.
Yeah, one circuit you can. Like it's the amount of freedom there is, right? Like of course you can globally define whatever circuit you want to be. Like if I give you bit 0, then it's this complicated circuit. It's predetermined, but that doesn't. It's more about the distribution, right? It's not one circuit. Like you have too many states that you want to specify, so you cannot do it with.
I didn't understand the definition part, because QMA complete problem when we saw, then they were verifying. I mean, the certificate was the quantum state itself, right?
The difference is between the input and the certificate, right? So the certificate can or can't be quantum, but the input of the problem is classical. So for example, if it's the Hamiltonian problem, local Hamiltonian, whatever, the description is the Hamiltonian itself, right, which is classical. Okay?
So here input.
Yeah, here the input we are taking to be this side, right?
Yeah,
Because you want to distinguish a pseudorandom state from a random state.
Arthur will like apply the circuit and see if he gets the state psi or not.
Yeah, he'll do a swap test. So he applies the circuit on 0 and then sees, does a swap test with the state he holds, and if it matches, he outputs that he has a PRS. Otherwise, he outputs that he has a.
So inherently, he, like Arthur has a. So I don't understand. Arthur has a state psi with himself, right? So he can just.
That's the
input
problem.
this-
That's the problem instance. Yeah.
Yeah. So Arthur can put psi in the swap test.
Yeah. No. This construction is fine. I don't think there's a problem with the construction. The point is that this is not QMA. I mean, you're not able to relate it to QMA, because QMA as it is defined is for classical inputs. It's not for quantum inputs. You can define one with quantum inputs, but the whole point is that you want to understand the connection to known complexity classes. Right. I think people have done work with state QMA and so on as well. Like they define state QMA. I think is the thing that you precisely why the input is a state and you treat it.
So finding ground state of a Hamiltonian is a QMA. So I mean verifying if the state is the ground state of.
Yeah, not the search necessarily, but yeah, the decision. Yeah.
So like how do you describe the state over there, like for that problem?
No, the input is the Hamiltonian. You have to say whether or not it has a ground state with certain energy, right? So the input of the problem is just classical, and then that's what Uttam was also asking. The witness can be quantum, that's okay, but the problem itself is classical. Yeah.
But for n qubits, the Hamiltonian's description will be 2 to the n. So now
If you have, yeah, that's why we have local Hamiltonians, right? That's why we don't consider arbitrary Hamiltonians to make the problem not trivial. Okay. Great. So, okay, so one approach to addressing this question
PRS and how random is the distribution?
I forget. No, maybe 2020s. I think 21. 20. Yeah, there's been a lot of work since then. So. Yeah, what is worrying me is that I can't. I'm a little confused with one step of the proof somewhere. I don't know. Because the earlier version of this paper had some errors and they fixed it. Okay. So the question remains, right? We still want to understand how to connect classical complexity, like classical input, like proper language like classes here, and you have quantum input. So one approach is the following. So one possibility is to consider quantum adversaries that can query a classical oracle, okay, to some language. Right, so language is, remember, just a function from the set of all strings to 0, 1. So we're going to basically consider quantum algorithms that can query such an oracle, such a classical oracle. And now, if one can show that PRS can be broken, by broken I mean you can distinguish it from a hard random state. So by such an adversary, then this would imply that if PRS exists, then L is not in BQP. Right, so you get a separation from BQP. So what is this saying? This is saying that suppose you had access to some language L, okay, some classical complexity, you got oracle access to it, you're a quantum adversary efficient, and if you're able to show that given access to this oracle you're able to break the PRS security, then that would mean that if PRS actually exists, then that language could not possibly be in BQP, because just by oracle access to the language you could already break PRS. So if that language happened to be in BQP, you could anyway break PRS, right? But you're saying PRS exists. So. Okay, so this is the consequence. Yeah, but we don't expect PRS to be secure against exponential.
So suppose there was something else that was secure against exponential, like let's say EXP. Like, so given access to another language L which belongs to EXP, if it can be broken.
Given access to another language which belongs to exp, okay?
Yeah. So
and the adversary is what? Is also exp.
Adversary is also exp.
Okay, so the oracle is useless essentially, okay?
No, it's
if the language is in exp and I am already exp, then unless the problem depends on the oracle, or maybe I'm misunderstanding. Okay, say your question again. Okay, I am exp and I have oracle access to exp, then?
It is stronger than exp. It's like
exp to the exp, right? You can probably concatenate it, yeah. I think you need some kind of closed under compositions, because poly to the poly would still be.
this would work only for like poly.
Yeah, things that compose, I think, probably. No, what poly to the poly, n to the n to the n is also not.
It's not poly.
Yeah, it's not poly, yeah. So even for poly, it would probably not be true. But if I'm poly, I can only make poly many queries. So if the problem itself can be solved in poly time. Oh yeah, sorry, I was confusing the exponential notation. Sorry. If you're poly, you can make at most poly many queries, right? So the runtime would be, say you make t queries. So your runtime would be t times poly, right? Where poly is, Basically, the whole thing will be poly, yeah, because you're making poly many invocations. No, why? N to the n to the n is not. Oh, you're saying oracle? Yeah, exactly, yeah.
X power x plus naught x.
Okay,
Like
so
asking because
if I make exponentially many calls to an oracle that takes exponential time, yeah, you just have to multiply it, right? Like, so I can make exponentially many queries, and each query takes exponential time. So it would be whatever e to the t times e to the t.
query can also be exponentially sized.
Right, but I'll only be able to read. Yeah, I'm not sure if it matters. Yeah, we can look into it later. Let's not get distracted unnecessarily. Unless you have like something more concrete that. Oh, okay. Yeah, this we can sort out afterwards. I don't know from off the top of my head. I'll have to look into it. Anything else? Okay. Okay. So the story is the following. So so they show such a result. For L equals PP complete. Okay, so they show something like this.
So here adversary was polynomial and you gave access to a
Okay, so if somehow it happens to be the case that yeah, so yeah, I guess I've written what I wanted to say. I don't think there's much. Okay, so basically this says that therefore if BQP is actually PP, then PRS cannot exist. Right, it's an obvious statement. Okay, and so this is their first theorem, which we will actually not prove in class, so it's just good to have it written. It's an informal version of whatever theorem, 2.7 or 27, actually I don't know, 27. So it says there exists a polytime quantum algorithm augmented with a PP oracle that distinguishes PRSs from randomness. Oh, sorry, hard random states. PRS from hard random, right? Okay. So this is kind of straightforward, nothing very surprising in the sense that the formal statement doesn't contain anything more than what we already said. Obviously, the statement itself is very non-trivial. So, if you have PRSs,
where does PP lie in this complexity classes?
I don't remember.
PP must be
PP is the counting thing, right? So,
PP is BQP is within PP.
no, then this doesn't make sense. Oh, BQP.
yeah. It's like
Yeah, then it's okay.
yeah.
But do they know like separation, like strict separation? And I'm asking.
No, wouldn't that would probably separate P from P space?
so.
No,
So
because
okay, so it's at least bigger.
probably would it?
Otherwise,
I'm
this will
not.
not make sense. PP has to be bigger, otherwise.
No, it has to be bigger for sure. Like it's probably very big, but I just don't remember the exact relations where it sits in the polynomial hierarchy and so on. Yeah, I can look it up and tell you next time, or you can look it up as well. But
No, I was just wondering why they choose the oracle to be PP oracle.
yeah, I did not do the proof, so I don't actually have the intuition for why. Okay, so and then they continue. They're like, can we do weaker than PP? Okay, so perhaps QMA.
showed one separation kind of thing. Now they want to make it tight.
Yes.
So I need to know that where the complexity classes are.
Right.
So now QMA is supposedly inside PP.
What is post BQP equal to?
Post BQP with Oracle, I think
Isn't that PP?
No, it was very high. Post BQP, I think, was related to P space.
Yeah, this is a very standard result.
I think
Post BQP is post selection. It's it's a result by Aronson. It's a node. So yeah, okay. Yeah, so okay, so post BQP is PP. So I guess that gives you some handle on why they're choosing PP. Like the promise version. Okay. Okay, so now can we do weaker than PP, perhaps QMA, right? And it turns out that, so we saw already, right, we had that obvious sort of thing where it looks like it should be in QMA. So now this is instead of because QMA is a decision classical input output sort of problem, so we can give it Oracle access in a similar sense, and we can see if this actually works. But it turns out this is not true. It's not true in the sense that at least this approach will not work, so it's unlikely. Okay, and why that is because of the following. So there's an informal version of theorems 30 and 33. So we'll try to prove theorem 30 today, at least make progress towards proving it. So what it says is, actually no, I think misspoke. Yeah, so I don't think it's immediate. Okay, let me write down the theorem and then we'll see. Then let's see what it means. So there exists a quantum oracle O such that, number one, BQP to the O is the same as QMA to the O. Okay, so there is an oracle relative to which BQP and QMA become the same, they coincide. And yet, PRUs, so pseudorandom unitaries, and therefore also pseudorandom states. So we haven't looked at pseudorandom unitaries yet. I mean, we saw it in seminars and so on, but we haven't actually looked at it in class. But they're essentially indistinguishable from. Yeah, so we already saw hard random unitary, so it's just indistinguishable from hard. You give Oracle access and then, okay. So, the second statement is that PRUs exist even relative to O. Okay, so this is sort of the main reason why everyone got very, very excited about working in the foundations of cryptography, because what this says, yeah, let me actually just write down the story because it's written quite nicely. So because it has implications for crypto, right? So the crypto implications are as following. So no computationally secure classical crypto exists if BQP equals QMA, right? So if BQP equals QMA, what it means is that all primitives can be broken in NP, right? Because the whole thing is based on keeping some secret and expanding it, right? So NP is exactly that form. So if you have an oracle that solves NP, it can solve your problems, crypto hardness problems, right? And NP is already inside QMA. And if we have QMA equals BQP, which would mean that using the quantum computer we can essentially break any classical crypto, right? So, and what this statement is saying, that there exists a relativized world, right? You have oracles and so on. So it's not quite the real world, but this is still strong formal evidence where even if BQP equals QMA, you can do cryptography in quantum. So this was a pretty wild result, and then people got super excited about trying to figure out what is the weakest assumption that one needs and so on. Okay. No. The because is no computationally secure classical crypto exists. Sorry. I put the R in the wrong place. Yeah. Okay. So yet quantum crypto can exist, right? So that is, there exists a relativized world. Such that any computationally secure crypto must use quantum communication. Right, because if you're just sending classical messages, it can be removed.
There's this result that there is some relativized world where p to the power at oracle is the same as p to the power at oracle.
Mm-hmm.
So is there any rule taking classical?
No, but then you also have to show. I mean, the whole point is that. Yeah, with oracle, strange things might happen. So I mean, this is just formal evidence. So it maybe there's like some contrived construction one can come up with, where even if p is NP relative to the oracle, you can still have some primitives. No, but it doesn't make sense, because the whichever way you define the primitives, they can be broken in NP. Maybe I didn't answer the question.
Where I'm going is that there's also another world in which p is not NP.
Yeah.
Relative to the oracle. And this shows that relativization cannot solve p over c.
Yeah.
So is there like a known separation between BQP and QMA with respect
Oh, relative to an oracle.
there is, then this result will be weaker?
Yeah, this is just showing formal evidence for something. I mean, it's not claiming that BQP is actually QMA. It is, yeah. So you're not trying to address, you're not trying to see whether or not using oracles you can make progress in separating BQP from QMA. That's not the question that's being asked. So yeah, but actually don't remember. There must be some. I'm pretty. Actually, I'm not sure. I shouldn't say anything. I don't know whether we have oracle separation between QMA and BQP. Sounds like we should have, but.
It's possible. It's not possible.
Yeah, no, that's a good question. I should know. I'll add it to my list of embarrassments. Okay, good. So this is fine. So now let's actually. Yeah, so this is all there is for the motivation, because we were building commitments from pseudorandom states, right? So this was the reason why we were doing all of that. So now we're going to actually start with the prerequisites. So things will get formal now. Okay, so this is relatively quick, okay, because I didn't write down everything, because we've covered many things already. And there's one proof that I wanted to add, but I'm going to skip for now. I'll tell you the statement when it appears. Okay, so so what are the things we need from quantum information that we haven't really discussed as much? We did it like very early on in the beginning, which is the diamond norm, right? So this we haven't discussed. So if you have any channel or any thing that sends operators to operators, you define the diamond norm as follows. So it's the supremum. You take any density matrix, you extend the operator, and then you look at the one norm. Okay. And the Frobenius norm is, as you would remember, trace m dagger m. Uttam and I certainly remember. Okay. Fact 7 is that trace distance between A row and B row, where A and B are channels, is at most half A minus B. We are going to use this quite a bit actually later in the proof.
Surprisingly, normal Google search doesn't show accuracy present between BQP and
yeah, so maybe it's actually non-trivial. I don't know. Man.
There are separations between QMA and pH and so on, but not BQP.
Wow.
Or accuracy.
Yeah, there's also this QIP2 and QIP3, like the number of rounds of interaction. Anyway, yeah. These are all very cool things. I want to actually think about them at some point, but okay. And then fact 8, this is due to Aharonov, Kitaev, and Nielsen or Nissan. I don't remember. Sorry, I forgot which author n corresponds to. So it says let U and V be unitary operators, be unitaries, and suppose D is, and this is very interesting, D is the distance between 0 and the polygon in the complex plane whose vertices are the eigenvalues of UV dagger. Okay, so D is the distance between 0 and the polygon in the complex plane corresponding to the eigenvalues of UV dagger, this very strange object. So if you have this, then one can relate it to the diamond norm as follows of between these U's. So this notation is basically saying I'm looking at the channel corresponding to the unitary, right? So that's why I'm putting a dot. Because just writing U would make it a bit confusing potentially. So the diamond norm of this is exactly 2 square root 1 minus D square. It's so strange. So
Distance between 0 and polygon, is it like from 0 and center of polygon?
I suppose it's probably, yeah. I did not look at the proofs. I don't actually know the full definition, but I'm guessing probably the center, I guess. Distance actually normally is the closest point, probably. Yeah, it's probably the closest point. Oh yeah, sorry, the handwriting. So let U and V be unitaries. Suppose D is the distance between 0 and the polygon in the complex plane, whose vertices are the eigenvalues of U, V dagger. So I guess it's something like this, right? So if you have 0 here and this is the polygon, I guess you find the closest point, probably not the center, because that's how normally distance is defined, but I'm not fully sure. I didn't check.
Not the center definitely.
Yeah, makes more sense. Yeah, that's how we normally define distances to objects. But okay, so yeah, sorry for the confusion. And then there's this lemma, which I think, so this is we use this lemma, but I'm not going to do the proof because I didn't realize it will actually show up. I just wrote it down. So these are unitaries. So U and V are n cross n unitaries. Then it holds that U dagger minus V dagger, the diamond norm, is at most twice U minus V fidelity. Sorry, the Frobenius norm. So this is kind of interesting because you're able to relate the diamond distance to the fidelity, because I think in general this is probably not true, right? It's only true for
This is not fidelity.
not fidelity. Sorry, I misspoke. The Frobenius norm. Yeah. Okay. Okay, and let's straighten some notation that we'll use. So this is going to be, as you may have already guessed, right? So this is the channel corresponding to the unitary. We'll use. So if you have Hermitian matrices AB, A less than B basically means A minus B is PST. Oh, sorry, B minus A is PST.
That would be strange. I mean, there should be a dimension, square root of dimension factor. That's why it should be trace now.
Yeah.
In the lemma line.
That's what they've written. I hope it's not wrong. I didn't check. I mean, they gave a proof, I think, so we can look into it. I guess it's because of the fact that unitaries have special constraints on the eigenvalues, which is it basically follows by using this fact. So D was the distance, right? Somehow, so I guess you are able to bound the distance in terms of the Frobenius norm.
So if I just say triangle inequality in the definition of diamond norm, then I will get this kind of thing, but with the trace norm.
Right. Yeah. So I guess that's why they have to prove the strongest statement. And I guess what you're saying would probably hold in general, right? For arbitrary operators and somehow. Well, I don't know. Okay. So for channels A and B, or super operators, I'm not writing super operators. Like I'm not writing the word super operator, just using the word channels. Okay, so A less than B means that B minus A is completely positive. Okay, but this actually I don't think we really need, so you can skip. There is a nice characterization. So completely positive we know, right? So completely positive is that so lambda is completely positive. So completely positive. This is the definition is you do this, right? So this is positive for all rho positive, right? That's the thing. But what is nice that they show in the paper, I mean they observe in the paper, it's a result by Brandau, Harrow and Hradicki. So some of you might know. I'm just stating it because I thought it might be nice to know. So these are the maximally entangled states, and you want this to be positive. So this is like the usual notion of PST. And this is the maximally entangled state. Got it. Yeah. I had read it at some point, I'd forgotten. Okay, good. So this is Choi-Jamyukovsky you're saying?
No, the isomorphism is different, but the fact is related.
I see.
So this is the choice state. So a channel is CP.
Oh yeah, they're able to make it into a matrix, positivity of a matrix. Exactly. Good. Thank you. Good. So this is, but I didn't know that these guys are the first to show it. Brandau, Harrow and Hradicki. Okay. So Brandau, Harrow and Hradicki, 16.
I don't think they are the first.
Yeah, because it's Choi-Jamyukovsky is very old. So I guess that he must have read it in that paper and he cited them, I
Yeah,
guess.
exactly. Because in 60s already crossed that.
Exactly. Excuse me. Alrighty. So that's what we had for the trace distance and diamond distance and so on. Sorry, diamond distance and fidelity and so on. Now we're going to look at the Haar measure and concentration. Okay. So we are going to use S for pure states, and dimensional. U is going to be unitaries, so that's not surprising. Sigma sub n is Haar measure on, maybe I should actually write it. So these are unitaries, n cross n, unitaries. this is the Haar measure on pure states Sn. So we write that as sigma. Mu is going to be the Haar measure on unitaries. So Haar measure on unitaries. So this is just the notation, and so far everything is kind of standard. Now this is a little bit different. So they're using the notation un to the capital M. So this is the, so basically it's just m tuples of n cross n unitary matrices. Okay, which you can equivalently think of as mn cross mn matrices block diagonal. So each block is n cross n. Okay, so it's just basically a direct sum of all of these. Okay. So yeah, so it's u1 o plus u2, if you like, u capital M, right? It's essentially just this. Okay, and then they're going to define a.
So algorithmically, this was a difficult step, like we encountered last year, that if you are given two unitaries, you want to write a circuit that will implement this direct sum. So, I mean, let's see how they use it.
I see. Yeah, I think they give it, like the Oracle gives it to them, and then yeah, let's see. No. The Oracle gives you a unitary of that form with the O pluses. Not that it gives you unitaries individually and you're implementing the direct sum of the unitaries. Okay. And then mu n capital M. So I guess you can extrapolate from the definition here, right? So this is just going to be it's a product measure defined as follows. So mu n to the m, u1 to um is defined as mu n u1 mu n um, okay, on un to the m. Okay, un to the m is what we defined over there. This makes sense, right? Okay, and this you interpret as a distribution over u1 XOR u1, right? Because it's just putting weights on these kinds of objects. Okay. Alrighty. Okay, so now we're going to state a theorem, right? So theorem 10, which we'll write in a second, is a concentration inequality on the Haar measure. So this is something, I think something very similar we saw also for the, wait, when did we see this Haar measure concentration thing? I think when we were trying to show the deterministic schemes cannot give you unclonable encryption. So we used all of this so we encountered this concentration thing at that point in the course. So it's essentially the same statement, okay? So stated in terms of Lipschitz continuous functions. Okay, and what is a Lipschitz continuous function? So let's quickly recall. So L Lipschitz is defined as follows. So for a metric space M with metric D, a function f from M to R, the real number, set of real numbers is L Lipschitz if for all x z in M we have that f of x minus f of y, the norm is at most L times the distance between x and y as per the metric. Okay, so this is very similar to what we did, like say, we defined f in a certain way, and L was the quantity in the norm, but he's writing it a bit more. Sorry, he's formalizing L Lipschitz explicitly as this property, and we just had it in terms of like a specific distance. So we had instantiated it in a specific form. Okay, so now theorem 10. So what did I write? Okay, so theorem 10 says given n1 to nk natural numbers, let x be this space, so it's the space of, not tensor, direct sums of unitaries from n1 to nk. Okay, be the space of block diagonal unitary matrices, right? And let mu be that measure that we had written, so in 1, I mean it's not exactly what we had written, but similar to what we had written, be the product of her measures on x. Okay. Now suppose that f goes from x, so this is the space of interest, to a real number, is, so suppose there's a function which you can prove is L Lipschitz in the Frobenius norm. Okay. So there's a function, you can prove it's L Lipschitz. The function is going from this set of block diagonal unitaries to a real number. Okay. Then for each t greater than 0, it holds that as long as you're sampling the unitaries from mu, so as long as you're sampling the unitaries according to this distribution, fu is going to be greater than the expectation of v sampled from basically how far it is from the average, right? It's like a tail bound that we've been doing. So the probability that you're going to be, you'll get a value which is average plus t greater than that is going to drop exponentially in how far you are. So exact, the quantitative values are here. Okay, so it depends on the Lipschitz, how Lipschitz the function is. It depends on the dimension.
What is n?
Yeah, that's a good point. I think n I forgot to write. I think it was the max or the min, I forget. Is the worst case, right? So you have to make the distance, it's probably min, so I think n is min of n1 to nk. Yeah, it is. Actually, I have written it, I forgot to mention it where. Okay, and what was t? Oh, t is the parameter you chose. Okay. So the expression makes sense, right? Like the farther you go, the less likely you are to have that value taken by the random variable.
Provided you have good L, right?
Yeah, of course. Okay, very nice. Now we're going to formally define very quickly promise BQP and promise QMA, because we're going to use the definitions. Yeah. Okay. So 2.5 is complexity theory. Okay. So just so that there's no confusion, let's define this. So a language is a function L from 0, 1 star to 0, 1, right? So this is okay. How do we define a promise problem? So promise problem is just a function pi, right, that goes from, it's the same, okay, but you have to add one extra output, right, because it can be undecided, so you add a bot. For some inputs you have no idea what's happening, and then we define the domain of pi to be x's, all the strings, such that pi of x is either 0 or 1. Okay, so that's so a promise problem is also defined just the same as a language, except that you have some inputs on which it can output perp if it wants. Okay, so using this we can specify what promise BQP is. So a promise problem pi from 0, 1 star to 0, 1 perp is in promise BQP if there exists a randomized poly time, this right, quantum algorithm A of x, such that if pi of x is actually 1, then probability that you get 1 from the algorithm on input x is at least 2/3. Okay, and the second one is, of course, if pi of x is 0, then this probability has to be at most to 1/3. You just need like a constant bound, so this is fine. And then BQP is basically, yeah, how would you define BQP now, given promise BQP?
All yes and no instances become 0, 1 star.
Huh?
If at a union of all the yes and no instances should become 0, 1 star.
No, that it's a promise problem, right? So it may not. That's the whole point.
No, you said you want to define BQP with all promises.
Yeah, exactly. So promise BQP is a set of promise problems, right?
Now if I remove perp, then it will become BQP.
Exactly. So it's a subset of promise BQP, such that the promise problem has no perp output.
Yeah, that is equivalent to saying that if I take all the yes and no instances, take union, then it will not be 0, 1 star.
If you take all the yes and no instances of a specific problem, right? Oh, yeah. Okay. I see what you're saying. Okay, I didn't pass it the way you were passing it. Okay. Yeah, that's exactly right. Okay, so BQP is the set of languages in promise BQP. It's a very nice and clean way of stating it, which is sort of cute. Okay. So now definition 12 is promise QMA. Okay, so again, so a promise problem pi 0, 1 star in 0, 1 perp is in promise BQP. Sorry, promise QMA if there exists a polytime quantum algorithm V, it is also good to set up the notation. So V psi. Okay. So this is a verifier, and they should exist a poly P such that you have completeness and soundness, right? So completeness is if pi x is 1, there exists a witness, so there exists a psi on px. So that's the only formalization, that you also have a polynomial that tells you the size of the witness. That's the only extra thing that we're adding here.
So could you explain the first time that BQP is a set of languages in Promise BQP?
Yeah.
BQP is inside Promise BQP.
Yeah.
They are not equal, right?
No.
So how do I understand this statement?
Language is here, right? That is exactly what you were saying. There's no perp, right? So you just take those problems that correspond to the language, not necessarily. Right? Yeah, it's nothing very deep. Huh? It's just using the definition of language. Huh? Okay. So now, if pi x is 1, there exists psi on pi x. Now, such that the verifier accepts, right, with probability at least whatever 2/3, such that probability verifier accepts psi, right? Oh shoot, is at least 2/3, and then if so, this is completeness, this is soundness. So if pi x is 0. Sorry, I'm writing very quickly because you know all these things, but it's just good to formalize it once because we'll use these definitions. Okay. Huh? Yeah. That's why. Yeah, we can. Yeah. For QCMA, the certificate may be classical, and your computation is. Yeah. For QCMA, it has to be classical. Sorry. Here it may or may not be classical. Okay, and the probability that the verifier accepts psi A is at most 1/3. Okay, and then QMA is the same. It's QMA is the set of languages. Is the set of languages in Promise QMA. Okay. So we'll not need post BQP and Promise PP because we'll not cover that part of the proof. Okay. Very nice. And now we finally have to set up the model because they're using quantum oracle queries. We'll formalize a little what a quantum oracle query actually corresponds to. So let's do that very quickly. So this is section 2.6. Specifies what quantum oracles are. I think there's also one section that I had to add later because I forgot to. It was about probabilities that was actually used later. So okay, we'll do it. Okay, so the convention is define queries to a unitary matrix U to mean a single application of U, U dagger, controlled U, and controlled U dagger. Okay, and so this one can write it as identity O plus U. We are basically applying identity O plus U, and this is the other one. So it says the dimension is the same. Okay, and this is identity O plus U dagger. So so you know, think of the C naught, right? So the C naught is basically like that, right? So it's 1 1 and then 0 1. So it's because the qubit basically just doubles the subspace you can control on it.
So query would mean all these things.
Yeah, exactly. So a single query means that you're either apply you either apply a U, the inverse, or a control U or a control U dagger. That's what they mean by a query. That's the model they're considering in the paper when they're talking about quantum queries. Okay, and then superscripts, right? For algorithms, which I got confused about like an idiot. For algorithms, okay, I think I just messed up the. So superscripts are basically just going to denote algorithms that have Oracle access. So you know, so we write it as a superscript. So A has Oracle access. Right, this is completely fine. It's pretty standard. And then, so we'll also define variants of promise BQP, promise QMA. With oracles, right? So what this means is that, so more precisely, the algorithm or the verifier, right, depending on whether you're in QMA or BQP, gets access to so this is sort of nice. Let me write it down. So you get access to a sequence, because you don't get access to one unitary, you get access to a sequence of unitaries. Okay, and the cost is the following. So cost is n to query okay, so not all unitaries cost the same, so it's going to cost n if you want to query the nth unitary. Okay, so basically this means that
What does it mean by cost? Is like query cost. Right?
yeah, query cost, yeah. That's the only thing we are concerned about here. Right? Okay, so this basically implies that polytime algorithm, right, on input x can query un for n equals poly size of x. Okay, and query is like in this sense that we already said. So that's the model that they're looking at. Okay, and so there are some small notes as well. Let's quickly write them. Time flies. It's crazy. Okay, so classical oracles are special case of quantum, right? Oh my god, so classical oracles are special cases of quantum oracles, right? So the convention that's used is that for L, so this is a language, a query to L is implemented by, you know, the way we usually do it, so implemented by the unitary as UXB is going to be XB XOR LX, right? That's just the standard reversible way of doing things. Okay, so that's good. Section 2.7 is the background from crypto. So definition 15 is PRS. This we already saw in the previous lecture, so we will not do this. We look at pseudorandom unitaries now. So definition 16, pseudorandom unitaries. Okay, so so we let kappa be a security parameter, and we let n of kappa be the number of qubits in the quantum system. Okay, so a keyed family of n qubit unitary transformations uk k in 0 1 kappa is pseudorandom if the following conditions hold. So the first is efficient computation. So efficient computation says that there exists a polytime quantum algorithm G that implements, or I'll just write it directly, G such that G acting on, so you give it the security parameter and you give it the state psi, and it essentially implements the UK on psi. Okay, so this, so far it's just straightforward, nothing very deep. And the second one is so this is computational. Maybe I should write it in maybe I can write there, it's a little easier. Okay. Right. And the second one is computational indistinguishability, which just says that, you know, for any polytime quantum algorithm a to the u that queries n qubit unitary u, it holds that the probability that you sample k from 0 1 kappa, a, you took the unitary from you know, it's a Haar measure. No, sorry, you took it from the family, right? Because the family is here, and you sample a k uniformly at random. You give it the security parameter as a binary output. Probability that it outputs 1 is going to be the same as you take a unitary from the Haar measure. Okay, and yeah, we want this to be negligible in kappa. Okay, so this is fairly standard, fairly expected. I don't think there's anything complicated here. Okay, so here's a quick remark. So they're going to take n kappa to be at least log k. Okay, so the number of qubits is at least log k, and the reason is that if it's smaller, then one can do tomography, and basically you get a classical output. So you can do tomography. So if the number of qubits the unitary is acting on is you know, smaller than log of the security parameter, right? because everything is scaling in the security parameter. So if the system is too small, if it's log depth, I'm saying log many qubits, then you can just do process tomography and figure out the explicit description of the unitary. So you need at least this much to have anything non-trivial. And the second thing is that the type of adversary that we are looking, so type of adversary A, in both definitions that we looked at, so I mean we didn't look at the previous one, definition 15 and 16, so we take it to be non-uniform, okay. Is non-uniform with classical advice. Okay, so what that means is that you know, A gets the security parameter and it gets X, where X is the advice, and it can be of length poly in K in the security parameter. Okay, so these are the kind of adversaries we look at. So in addition to whatever input they're getting, they'll also get access to this this advice. Okay, good. Right. So now we do something much more complicated, which is probabilities. Okay. So this is a very cute lemma which says that Bayes' decision rule is optimal. So suppose that okay, so let X be a binary valued random variable, and suppose Y is a random variable, could depend on, okay, so it can depend on X with domain D, and there is some function that goes from the domain to 0, 1. Okay, so you have some way of assigning from the value of the random variable 0, 1. Okay, so basically this f you should think of as using y to reduce x. Okay, so f is the map, so you see the outcome y, it's telling you what x must have been. So the statement is that the probability that f of y equals x is at most argmax x probability x equals little x given y is x. Okay, so what this is saying is that you have the conditional probability, right? The guess you make is the one that gives you the highest given the y. So you know, if you take the conditional distribution, you'll have a probability for the different elements x, given that you know y. Okay, when you take the argmax, so this is the best you can do. Okay, so basically saying Bayes' rule is optimal. Okay, and then we'll prove one more lemma. Oh, sorry, we'll state one more lemma, which is used towards the end of the proof. Okay. So lemma 6, this is called the Borel-Cantelli lemma. What it says is that suppose that x sub n in natural numbers, so suppose this is a sequence of not necessarily independent random variables, okay, with values in 0, 1, okay, and if it so happens that we have this bound, so expectation xn is at most infinity. Okay, so basically saying somehow if x is an indicator variable of whether something happened or not, right? So you're saying on an average, finitely many things happen. Okay, so if you know this, then the probability that finitely many things happened is 1 essentially, or the probability that infinitely many things happened is 0. So if on an average you know some quantity is at most infinity, then you can deduce that finitely many things happen with probability 1. Okay. So okay, good. I think we can make some more progress. All right. So now we can actually start our actual result that we want to prove. Okay, so this is section 5 now. Pseudo-randomness from a quantum oracle. Okay, so what we're going to do is, so we construct a quantum oracle u comma c, okay, relative to which, like we said, right, promise BQP is going to be promise QMA, and PIUs will still exist. Okay, so that was the, the promise or the assertion we made at the beginning. The only difference is now we are actually being more precise and talking about promise BQP and promise QMA. So we first describe the oracle. Oracle, okay. So it has two parts. So U is the quantum part. Okay, and C is the classical part, or a language basically. Okay, because when you're looking at so since we are looking at oracles, right, they can be arbitrarily powerful, right? So there's no bound on that. So really we can just think of it as a language if the input-output is classical. So that's why I'm just calling it a language. While here it's not obvious, right, that it will be a language, which was the issue I had mentioned, because it's a unitary, so it could be taking quantum inputs and producing quantum outputs. Okay, so let's start with the definition of the oracle. Right, how does it work? So the oracle U at least is straightforward. C is the complicated one, which I guess we'll do next time. So UN is basically the following. So it's defined to be a sequence of UNs, where for each n, UN is sampled from the Haar measure on 2 to the n qubits, and you take a direct sum of 2 to the n many of them. Okay, so that's just to say that UN is a direct sum of 2 to the n different n qubit unitaries, n qubit Haar random unitaries.
query this oracle once, then it will implement this big unitary.
Yeah. So U1 is just going to be a single unitary acting on one qubit.
Yes.
U2 would be 2 unitaries, well 2 to the n, 4 unitaries.
No, I mean,
4. Yeah. So n equals.
qubits, yeah. So unitary will act on 2 qubits.
Unitary acts on 2 qubits, but there are 2 to the n many unitaries.
So there will be 4 unitaries.
Yeah, so there are 4 unitaries for n equal to 2. Like there will be a direct sum of 4 unitaries. That would be like this. So this is what U2 would look like. U1 would just be 1 unitary acting on one qubit.
Input, then I cannot apply arbitrary value.
Yeah, but this we already observed, right? Where we had it written over here that you're given, because you remember we were talking about the cost, how we were counting it.
So for UN the cost is n. You wrote it for UN the cost was n.
Yeah, so you will not be able to access more than many. Oh, you're saying that even the number of unitaries is also growing. Yeah, that is true. Yeah, it's a different point. Yeah, you're right. Yeah. Yeah, let's keep it in mind as we go through the proof. Let's see what they're doing. Oh shoot, it's time, so we should stop. Sorry, I didn't realize. Okay, yeah. So next time we look at C. I think the language C is where it gets interesting and.